people have died, spaceships have crashed, and students' grades have gone down because of a mix-up of units or units that have been completely forgotten about. And the units are very basic, but it's very important to have a really strong foundation and to go over the basics and the fundamentals so that there's no gap in knowledge. So we're going to go over units, conversions, and the mole. Now there's an internationally accepted set of units called SI units, which stands for, and this is French, Système International de Units. Sorry, horrible accent. Your prof may call them standard international units as slang, but this is what they stand for here. Now there's 7 base SI units, and they are seconds for time, meters for length, kilograms for mass, amperes for current, Kelvin for temperature, mole for amount, and candela for luminous intensity. And those 7 base units kind of form the basis of dimensional consistency. Now, of those 7 base units, there are 22 derived units, which come from the base units. And these are the ones here. Now, we're not going to go over all of these, but just note that all of these derived units come from the base units. And the ones that we generally use in thermodynamics is joules, newtons, degrees Celsius, pascals, and then maybe watts, hertz, volts, and coulomb. And it's a lot more convenient to use these derived units sometimes than base units. And we can use them kind of mix and match. So if you're in derived units, then it's implied that you're also in the base units. For example, 1 joule is a Newton meter, which is a kilogram meter squared per second squared. So if you're in joules, then you know you're in the correct base units right here. Same thing with pascals. 1 pascal is a Newton per meter squared, which is 1 kilogram per meter second. Now, the only odd derived unit out here is degrees Celsius. You just can't put in degrees Celsius for Kelvin when you're using absolute temperature. It only works for a change in temperature. Okay, so a physical quantity is something we want to measure, like some property, mass, volume, temperature, whatever. That equals its number times the unit. The number is literally the number, the numerical value. So for example, the physical quantity of mass has the variable m, which is the number 1.2, and then the unit of grams. Couple things to note. This triangle is a capital delta. It's a Greek letter delta. It means change, and change is the final minus the initial. So delta E means the change in energy, which is the final energy minus the initial energy. And it could be the change in anything of what we want. Another very important thing is if you have the unit to some power, then the prefix is also to that power as well. It's implied. So milliliters cubed means that you also cube the milli. Milli is 0.001, so you're cubing that as well. So this becomes 1.2 times 10 to the negative 9 liters cubed. And also a note, something that a lot of people don't do, is you want to have a space between the number and the unit. It just makes it easier to read, and that's kind of the accepted convention. We have spaces between words. No space is hard to read, so have them between your numbers and your unit. Okay, so for unit conversions, we want to treat units algebraically, so just like numbers. One of my favorite ways is to start with the goal unit and then convert everything else from there. So let me show you how this works. So here's an example. You're throwing a pizza party for 15 people and figure that each person will eat 4 slices. Each pizza will cost you $14.78, and it'll have to be cut into 12 slices. So here's our question. How much is the pizza going to cost you? You only have $70. Will you have enough? So there's a lot of numbers here, but we want to search for what we're trying to get. And this is our desired unit here. How much is the pizza going to cost you? It's dollars, so we're going to start with dollars. And we don't want to start with the $70 because that's what we're comparing it to. We'll start with this $14.78. That's how much it is per pizza. And as long as we cancel out pizza in the right way, then we'll have the unit we want in the numerator right here. Now, pizza, what do we have for pizza? Well, each pizza has 12 slices, so that's what we'll write down here. And we'll put pizza in the numerator so that it cancels out, and we have slices in the denominator, 1 pizza for every 12 slices. Now we have dollars per slice here, right? Dollars for every 12 slice. Now we want to cancel out slices, and we're given 4 slices for each person. So we'll write that there, 4 slices for each person. Slices cancel out. Now we're in dollars for each person, but we don't care how much it costs per person. We care about how much it costs for the whole party. And there's 15 people for the one whole party. And if we write it this way, then person cancels out with people, and we're left with $73.90 for the party. So we don't have enough money. Okay, so here's an example. A typical football team has 53 players. Assume that each player can eat 1.5 hamburgers per hour. If each burger weighs 220 grams with a density of 1.24 kilograms per liter, what volume in liters of burgers can the players eat in 2.5 hours? Now there's a lot of numbers going on, but we're just going to search for our desired unit. And it's asking here what volume is in liters. So that's our desired unit. And which of these numbers has our desired unit? Well, it's this one right here, 1.24 kilograms per liter. So we're going to start with that. Now this is the wrong way because we want liters. So we need to flip this conversion to have liters in the numerator and kilograms in the denominator. And now our goal is just to cancel out kilograms with everything out so that we know how many liters it'll be for the whole team. Well, what do we have with a mass? The number with the mass is 220 grams. Now grams doesn't cancel out with kilograms. So first we'll convert kilograms to grams, and we'll multiply 1 kilogram for every 1,000 grams, and then multiply that by 220 grams for every one burger, which is what we're given here. And kilograms cancels out, grams cancels out, and now we're in liters for every burger. We need to cancel out burgers with something, and we'll look around that each player can eat 1.5 hamburgers per hour. So we'll do that, 1.5 burgers for every hour for each player. So that's all for each player. So burgers cancels out. Now we're in liters per hour per player. But we don't care about for every one player, we care about for 53 players. So we'll multiply this by 53 players and the 2.5 hours, because that's kind of our duration, which players cancels out, hours cancels out, and that gives us 35 liters. It's a lot of burgers. Okay, the mole. So the mole helps us count things that are really small, or that there's like tons and tons of things, and it's the standard unit for counting molecules and atoms. And we're used to using groupings to count things. Like the most common maybe is the dozen. 1 dozen is 12, so rather than say 12, you can say a dozen. Rather than write out 100, you can just say the word 100. Million stands for 10 to the 6, and mole, just like that, stands for this number right here, 6.022140076 times 10 to the 23. And it's literally a number. This is kind of like a weird number. If you want to know where it comes from, you probably never need to know. But historically, the mole was defined as the number of atoms in 1/16 grams of oxygen. Seems like an also random number, but like way back in the day of John Dalton, an atomic mass unit was 1, and that was ascribed to hydrogen, and they tried to make it as close as they could to that. But then when isotopes were discovered, this 1/16 grams of oxygen didn't really work, because the amount in moles changed based on the isotopic composition of oxygen. So it was redefined as 1/12 the gram of a carbon-12 atom. And there was another redefining of the mole, which they said, rather than basing it off something, we'll just say 1 mole is 6.022140076 times 10 to the 23 of entities of anything, and just define it that way exactly. And that's what it is. So it's 6.022140076 times 10 to the 23 of whatever we want to count. It can be atoms, molecules, particles, things like that. So a mole is a number, and it's also an SI unit as well. And kind of on the side, Avogadro, kind of the way they picture him, his most famous picture, makes him kind of look like a mole too, doesn't it? Anyways, let's do some examples. So a patient has 50 germs in their teeth. How many dozens of germs are there? Rather than using a mole, we'll start with something very common, is with the dozen. We'll count how many dozens of germs there are on this patient's teeth. Looks pretty clean, but actually there's a lot of germs. And we'll say how many dozens. Well, there's a dozen, There's another dozen right here. We got a third dozen and then a fourth dozen right here. So there's 4 and 2/12 dozens, which is 4.17 dozen. So that's how many there are in the units of dozen. Okay, now we'll do an example of counting by grouping using the mole. And this is our example. A silver ring has 8.1 times 10 to the 21 atoms in it. How many atoms in moles is this? So this is a conversion question, and it's asking us how many moles there are. So that's our desired unit. So we'll start with moles. So we'll use our conversion with moles so that moles are on top because that's what we want. And then we have the other unit, the number, on the bottom. Now we got to cancel this out. So there's this many atoms, but we're given 8.1 times 10 to the 21 atoms. So atoms cancel out, which gives us 0.013 moles. Perfect. Now, molar mass is the mass of 1 mole of substance, which could be anything, an element, molecule, compound, whatever. You just have 1 mole of it. And the units are usually in grams per mole. But if you need things to be in SI units, then kilogram per mole is what we need our molar mass to be in. So here's an example of a unit conversion using molar mass. How many hydrogen atoms are there in 34 grams of ammonia, which is NH3? And we're given the molar mass of ammonia is 17.0 grams per mole. So we're converting stuff. What's our desired unit? It's this right here. How many hydrogen atoms? So that's what we'll start with. We have mass of ammonia, 34 grams, and then we have this other conversion here, 17 grams for every 1 mole. So we'll start with the amount because that's what we want. And this is how many hydrogen atoms there are for every 1 mole. Now we need to cancel out moles until we get to the full 34 grams of ammonia. Well, we're given, this is moles of H atoms, right? And if we look at NH3, there are 3 moles of H atoms for every 1 mole of NH3. Like, think of this as like 1 molecule. If you have 1 molecule, you have 3 H's. Well, if you have a mole of molecules, then you have 3 moles of H's, which is what we have here. Okay, so now we have the units of moles of NH3 in the denominator. We need to get to 34 grams, so we got to convert moles to grams. So we'll use this conversion right here, and we need to cancel out moles. So we'll have moles on top, 1 mole of NH3 for every 17.0 grams of NH3. Moles cancel out, and now we can multiply by the 34 grams of ammonia. That cancels out to give us the number of H atoms, 3.6 times 10 to the 24 H atoms to 2 sig figs. Great. All right, so there's a foundation of units, kind of very basic, but we just wanted to make sure that there's no gaps. Good luck on the rest of your studies. We're going to build up our knowledge and get into the more complex material. Hang in there.